Hi girls and guys, my name is George. What my colleagues Jeremy, Rob and I are going to show you is various activities and key knowledge ideas in towards the mathematical field of geometry. What I'm going to be exploring is the angles component of geometry. Angles come into the geometry at Oswald's level 3 and they continue to level 6 and beyond throughout the higher year levels. However, what we're going to be only focusing on is the primary level of geometry. So according to Bobbis, Mulligan and Laurie, it is important to first recognise superficial similarities between angles, and these are based on physical angle situations such as the angles of tiles, hills and also wheels. So some learning objectives for these tasks in regards to angles is to visually identify the differences between the types of angles, which includes the ones that are equal to, greater than or less than a right angle. And we also want the students to be able to estimate, measure and compare the angles using the degrees. So for our first activity, we've just got a selection of shapes here, and what we're going to do just onto the page is that we have our shape, which Jeremy has already pre-drawn, and using a protractor, what our task is to find the angles inside the shape. So acknowledging the corner piece is 90 degrees. So what I also want you to do there, Jeremy, is just to write down the degrees. Okay, yep. That's it, and then on to the next angle. Just to 30 degrees. And then annotating the page to also find the other angles. So that comes to 60 degrees. So also what you should also get your students to do is to identify which angles are right, obtuse or acute. Okay, so obviously we have one right angle and two acute angles. So some prior knowledge for those activities that we just did was to identify what kind of shapes were being used. So on the page, utilising maybe a cross or an arrow or the triangle that we used. And also knowing the properties of an acute, obtuse, right or even a reflex angle. Okay, so one computer website that I found that utilises an online protractor is AmblesidePrimary.com. And the beautiful thing about this is that it actually shows a teacher's controls. Okay, so you have the option to show the angle, etc. So we're going to start off with up to 180 degrees in 5s, and what that means is that we actually have a shape here, an angle, and we've got to utilise a protractor, and we're going to basically put that right in the corner, this basic bit right here, the centre point. And the common misconception is to where to actually place the protractor. Some students might put it up here to try and find the angle. However, we want to put it right into the centre, and using these buttons down here we can move around the protractor to the right angle and to find that this is at the base, and then we go up to 80 degrees. So in this bottom box, type in 80 degrees, check, well done, and we get to move on to another one.
So today's lesson, what we're going to be looking at is the geometric lesson of translation, rotation and reflection. Oswald states that this lesson can effectively start at level 2, but today's focus will be on grades 4 to 6. Focus on 4 to 6 being basic line of reflection on graph paper. So when we move to the 5-6 levels, we're going to start using the Cartesian plane with all coordinates, all 4 coordinates, x and y, negatives and positives. As Booker suggests, IT is a good starting point for these type of activities because it gives students the ability to manipulate objects through technology, also bringing in an aspect of IT. These activities rely on an element of student prior knowledge covering from angles of degrees, turning, rotation. So another form of prior knowledge that students should have is grade 5-6 students should be able to work with Cartesian planes quite effectively and know what the quadrants look like. Moving through to common misconceptions found within this topic, what Booker has found within his textbook is that students often have trouble connecting the names of translation, reflection and rotation to the actual action put place on graph paper. A prime example of a good IT program to introduce students to translation, reflection and rotation is Maths Transformation Program found on sciencekids.nz, which is an educational website for students.
We just have George giving us an example of what will happen if they select
so
it.
See George on the thing, like, so do one that's wrong or not. That's fine. So the good thing about this program is that it shows students what each function does and how it works, whilst providing them with the ability to manipulate these objects electronically. So this program is also particularly useful because it caters for all age groups and abilities. So students at level 2 can use this program as it's quite simple, and students in grade 6 could also use this program because it allows students to use their own coordinates on these Cartesian planes that you can see. Yeah. A good follow-up activity after introductory activities like we've seen on the IT program is to just get students to cut out their own manipulatives and create a line of reflection as seen on the graph paper represented by a red line. Students are then to outline these manipulatives and try to reflect the original object across the line of reflection. And as we can see, George has just made a mistake, which is part of common misconceptions, and just moved the object when instead he should have done something like that to show a mirrored object.
Isn't it?
Like that.
That way.
As we saw, Jeremy still has misconceptions.
I'm sorry.
This is a correct reflection. So basic rotational activities that 5 to 6 students can work on is just rotating these manipulatives at regular angles of rotation such as 90 degrees, which George will now show us. The main point of these activities is to have the student put their finger on the point of rotation, which can lead to some common misconceptions where students aren't quite aware of what the point of rotation means. So then when we're moving on to translational type activities, what we'll start with is manipulative being at a basic point, such as this, and we're tracing it. After completing the tracing, what we'll do is we'll translate the object at a basic movement. So for this example, George will move it 2 units to the right, and he will trace this new shape to show how far the original shape has moved.
Just change colour.
The purpose of these tracings is to show the students how the original object is actually moved and give them a greater understanding of the function of translation. So today's learning intentions for my lesson was to increase student understanding of geometric reasoning. And the specific learning goals for today's lesson can be found within OSVALs, as it is an activity that's more designed for the later years of primary school. Level 5 and level 6 have a clearer understanding of what we're trying to achieve. So for level 5, we've got describe translations, reflections and rotations of 2-dimensional shapes, identified line and rotational symmetries, which I think we completed during the activity which George demonstrated. For level 6, we've got investigate combinations of translations, reflections and rotations with and without the use of digital technologies, which again draws back to the IT program that we were using, as well as the activities that George completed.
So for this lesson today, we're doing geometry and shape, and what we'll be doing is exploring 3-dimensional shapes. Shape comes into the OSVALs from early foundation, but the shape that relates to it today from year level 3 is knowing how to, or constructing 3-dimensional objects such as simple prisms and stuff like that, and being able to talk about basic features. but what we'll be focusing on today is level 5 to level 6, which is knowing the features of three-dimensional objects in a more mathematical language type way. So according to theorists like Bovis and stuff like that, it is important that kids explore shape not just two-dimensional but three-dimensional and see it in very different ways. The reasoning for that is because in our modern world, two-dimensional and three-dimensional shapes are constantly blurred with what we can do with technology and other malleable products that can alter perception of children so that they don't have that key construct as much. So prior knowledge for this area of mathematics, if you look at Van Heil, the theory of relating shapes as families is all part of three-dimensional shapes as well. So children need a firm understanding of two-dimensional shapes in the first place, the families they belong to, and how to recognise what a 3D object is, such as a cube. So realising the basic shapes in a cube, such as it has 6 square faces and so forth, or a triangular pyramid might have, hang on, 1, 2, 3, 4. So 4 triangular faces. So you need to understand shape and need to understand that it's obviously 3 dimensions means a solid object, so it has depth, width and height, not just a 2-dimensional object that you draw on the paper. So as Bovis et al. Suggests, it's important for children to understand that 3-dimensional shapes contain 2-dimensional faces. They also contain 1-dimensional lines and 0-dimensional, which are the points. So as we see, we've got a net diagram here of a triangular pyramid. So it's 4 triangles, and as a student puts it together, which is George, this can help increase the geometric understanding that a 3D shape is made from those 2-dimensional faces, as we had just a 2-dimensional piece to start with, and we have now made a triangular pyramid. This is also good because children are actually using manipulatives, they're making it themselves. Even though this is a simple shape, there are many other net diagrams that are a lot more complex, and a lot of children will have trouble from the start looking at the net diagram and understanding that it can actually make that shape. So as I explained before, the 3D shape is made up with 2-dimensional faces. So what you can actually do if you want to talk about the 1-dimensional lines is actually make a skeletal pyramid of the same shape. So we have George here. This is some toothpicks and some blue tack, which all kids can use, so it's another manipulative again to help them explore the mathematical concepts of shape and geometry. So if we lay it on the table, that's our 2-dimensional shape, and obviously George can build it up into a triangular pyramid. So as we can see, we still have all the same triangles as the faces, but now we can actually see the 1-dimensional lines. And as I said earlier, with the 0 dimensions, that is the points. So if we were to imagine these lines disappearing and just had the dots standing in space, you would only see those dots. Okay, Booker also mentions introducing technology into schools, as technology is part of everyday life. This is a website called Math is Fun, and it has a really good system to talk in looking at cubes and anything from polyhedrons to other maths topics. But this is quite good because this will actually show you the cube, so I can drag it around. You can see the 3-dimensional object, what it looks like, that it has the 6 square faces. You can see the net that can create that cube, and you can also explode it, so you can see the individual pieces separated to see how they join together to make that shape. Obviously the learning objective today was basically to show that students need to understand two-dimensional shape and how that makes up three-dimensional shape, or three-dimensional shapes are made from that, and that whether a shape is solid, so whether it's hard or hollow like this, or the skeletal version, they actually are the same, one and the same. They are a cube or a triangular pyramid or any type of prism. The same.